Dive into systems video series, in the systems programming video series, talking about the textbook Dive into Systems. We're moving on to section 4.5 on integer overflow. We talked a little bit about this before already, so I'll skip around a little bit. Now, sort of recall that an overflow is essentially when you exceed the bounds of what can be represented. Here in the textbook, they give this odometer example. I won't go through all the details, but, this is basically like an unsigned integer going from 0 up to 9. And by the time you hit a discontinuity, when you go from 9 down to a smaller number, right, in effect, kind of like if you add 1, you get something smaller, which is unexpected. That's where this discontinuity happens, and that is regarded as an overflow. Probably what we want to talk about here is that this is the diagram for an unsigned integer. There is no issue even throughout here, right? So like this jump right here, which, when we get over to talking about 2's complement signed integers, that right there is going to be a point of discontinuity. But for a unsigned integer, it is not, because you're going from, the representation of 7 to the representation of 8. There's no issue. The addition kind of flows exactly how binary addition should, taking you from one sequence of bits to the next sequence of bits. So no issue here, right? Long story short, no issue here. And the only place where a discontinuity occurs is here. So the lesson here, especially when you think about the carry. Let's go ahead and write out this number 15, and let's add 1. And let's think about the carry bits. So I recall that we talked a little while ago about the carry bits. And let's characterize the overflow for an unsigned integer in terms of its carry bits. Now, okay, in this particular case, we're going to get a 0, and then we're going to carry, and that's going to cause another 0 with another carry, and another 0 with another carry. With a 0 and a carry. This is an overflow, because as we said, this is sending us from the representation of 15 down to a smaller value. It's crossing this discontinuity. This is an overflow. Well, notice that this basically happens precisely when the carry in to the leftmost, most significant bit is 1, and it never happens when that So I think I misspoke there. What I should be pointing to is here. It's the carry out, right? Because there's a difference between the carry in and the carry out. So like, for instance, this had a carry of 0, but a carry out of 1. So there's this distinction between the carry in and the carry out, right? This had a carry in of 1, because the previous thing had a carry out of 1. The next thing has a carry in of 1. And then when you put them together, you get a carry out of 1, which then becomes the carry in of the next bit. And so anyway, long story short, this last bit has a carry in of 1, and then it caused a carry out also of 1. So if we wanted to characterize an overflow for an unsigned integer using addition, okay, this is a rule for addition. The rule is that that there is an overflow precisely when the carry out is equal to 1. That is different. I think, if I recall what we discussed in the previous video, we talked about the addition rule, which actually turns out to be, the addition rule for signed integers using 2's complement is that the carry in must match the carry out, right? So if the carry in and carry out are both 1, then there's no overflow. If they are both 0, then there's no overflow. But if you have one of them is 1, the other one is 0, it doesn't matter which is which. But if they're mismatched, then that is a simple signal telling you that there is an overflow for the signed integer addition that you're performing. So anyway, keep in mind that there are different rules depending on the different interpretations of these integers, right? The bits are the same, their length is the same, right? There's nothing different between the two systems except how any particular bit is interpreted. And so the interpretation can matter about whether or not an overflow has occurred. For unsigned integers, the rule is about just is the carry out equal to 1, and for signed 2's complement integers, the rule is about whether the carry in the final leftmost significant digit, whether the carry in matches the carry out. Different rules for the two different interpretations. So let's go through an example where we look at, and so here we're going to look at 7 minus 9. And while we interpret this as an unsigned integer, then this ought to, right, if you just kind of think logically about the little, sort of rotary picture, if you like, that if like 7 is over here and we subtract 9, it makes sense that we would get an overflow because we seem to be crossing the discontinuity at 0. So we should expect that when we compute 7 minus 9 in unsigned integers, that will cause an overflow. So let's see what happens when we actually perform the algorithm. So we're going to write them in bits, right, for bit sequences. And so we're subtracting them. Because we're subtracting them, recall that our rule for subtracting both for 2's complement and for signed integers was to take the number you're subtracting, bit flip, and set the carry in to the least significant rightmost bit to 1. And now we perform the sum of this. So when we perform the sum, then I think the point that they're getting at here is that this time the carry in to the most significant leftmost bit is a 1, and the carry out is a 0. Oh, I think I was missing what the book was saying before. I think the book now is, in fact, giving a different rule than what I initially understood. So rather than talking about the carry in and the carry out of, say, of some particular bit, I think it's talking here about the carry in and the carry out of the entire operation, right? In a sense, by setting the carry in of the least significant digit to 1, which is what we do when we're performing subtraction, you would maybe regard that as a carry in to the entire operation. And what you may do is think that the carry out of the leftmost, most significant bit is like a carry out of the entire operation. And so that's interesting. I never thought of that. That could be a way to characterize the overflow for an unsigned integer, right? So again, this is still the rule for an unsigned integer. We already talked about the rule for a 2's complement integer, which focuses only on the carry in and the carry out of the most significant leftmost bit. So just thinking about that one bit and its carry in and carry out, that's the rule for 2's complement. Here, I think they're presenting a rule where you give basically the same rule for a signed integer, except that rather than talk about the carry in and the carry out of the last bit, you instead talk about the carry in and the carry out of the entire operation. And then the rule is, again, that they must match, right? So since these are mismatched, right, the carry in is a 1, the carry out is a 0, they are mismatched for the entire operation. And so for an unsigned integer, this is an indicator of overflow. Then but now let's test this out on something that should not overflow. So if we think about, again, the picture where 7 is over here, 0 is over here, we subtract 5, and we should not, right? We should not cross the discontinuity. Therefore, there should not be a overflow. And so now let's see what happens when we sort of algorithmically decide this. So again, we represent 7 and 5 in binary. We are subtracting, so we set the carry in of the entire operation to 1. We go through the computations. Here, what is going to happen is there's going to be a carry into here. That's going to turn this into a 0. That's going to carry into here. That's going to turn that into a 0 with a carry out of 1. Now, to summarize and to see this rule in action, the carry in matches the carry out for the entire operation, and that is our signal that no overflow occurred. So that's interesting. I never thought of that, but that's neat. Just to give basically the same rule as the rule for signed integers, but rather than focusing only on a single bit, you talk about the carry in and the carry out matching for the entire operation. So I think here they're going to discuss the same thing that we've already talked about for the carry in and the carry out of the most significant bit. I'm not sure if they characterize it quite as explicitly. It seems like they give a little bit more of a maybe intuitive description rather than characterizing it in terms of the bit, right, the leftmost bit carry in, carry out. But in any case, or maybe they do, I'm just scanning it very quickly. In any case, yep, and then here's like a summary, a warning about the dire consequences of overflows, which, keep in mind, is not a hardware danger. It's not as though like somehow the circuit itself short circuits when there's an overflow or something. No, it's just that like the number gets truncated, and if you're not careful and you're not checking these things, then a number stored at some variable is going to be other than maybe what you thought it was, and then it produces weird behavior that's hard to debug. That's the risk here. This is a real risk. It can make your programs go wrong. It can make your Pac-Man game bug out. And I think, here you can get military service people killed with sort of truncated approximate values of the trajectory of missiles. Of course, right? Like, but I mean, that's kind of like your systems can sometimes be used for very important things, and so always get your systems right in every way, not just here. So, but it happens. So anyway, okay.